In this video, I'll be talking about factors affecting rate of chemical reaction, right? So, we said rate of chemical reaction actually has to do with the speed of chemical reaction. That is the speed of reaction that occur between two reactants, right? So, in that case, we'll be talking about factors that affect rate of chemical reaction. That is the rate at which a chemical reaction occur. And most importantly, all these factors, I'll be relating them to collision theory, right? Collision theory for better understanding of these factors. So, as far as collision theory is concerned, simply state that particles of reactants must collide together for a chemical reaction to occur. That is, particles of reactants must collide together, must collide for a reaction to occur. That is what collision theory simply means. But what I'm going to say is that I will be explaining everything about the factors that affect the rate of chemical reaction with respect to these particles of reactants must collide together. So what actually happens is that these factors will have to do with either increasing the rate at which particles collide together or decrease the rate at which the particles actually collide together. So that's actually what will happen. So from there we have different factors that actually affect the rate of chemical reaction. For example, we have the factors like the concentration of the reactants. We have concentration of the reactants, I'll be focusing more on this concentration of the reactants. That shows that this video will basically be based on concentration of the reactants. Now we have other factors, which is actually the temperature. I'll be focusing on that in a separate video. We are going to have another factor, which is the case of catalyst, right? And also we have another factor, which is actually the case of surface area. So we have the case of pressure. We have pressure of gas, right? Or we also have the nature of reactants. Nature of reactants will actually determine how fast a chemical reaction is going to be. So I'm going to talk about these factors, and at the same time I'll be focusing more on the concentration of the reactants. I'll be focusing more on the concentration of the reactants. So now let's start with the nature of the reactants actually. Now, one thing about nature of reactants is that we have three physical states of matter. Now let's say, suppose we have reactants A and B to give us product which is C, right? And let's say reactant A is actually in its solid state, right? And reactant B is in its solid state, and C is in its solid state. And let's say we have another reactant A in liquid state and B in, let's simply say, aqueous state, and we have reactant C in aqueous state. Now look at this expression. Now nature of reactant has to do with the physical state of the reactants, and it has to do with solid, liquid, and gas, right? And gas. And one thing about the properties of solid is that the particles in a solid form are actually tightly packed together, and that of liquid, they are actually they are not so packed, but they are also packed, but not like that of solid. But that of gas, they are free to move about. Move about rapidly. So they move about rapidly according to gas. But as far as liquid is concerned, particles of liquid are actually free to move about, but they are also very, very close together, but they are free to move about. So what the nature of reactants is basically talking about is that whenever particles exist whenever they exist in solid states, right, the reaction may tend to be very, very slow, right? So that's why the nature of reactant will actually determine the rate of chemical reaction. That is the rate at which a reaction is going to occur. And I'm talking about it related to collision theory. That is the rate at which particles of reactants will collide together has to do with the nature of the reactants. You cannot compare how fast a reaction is going to be when it is in gaseous state, compare with liquid, compare with solid. So nature of reactant actually affects the rate at which particles of reactants are going to collide together. So that's the first one. So now the second one, I'm going to talk about the surface area. Now let's go to the surface area. The surface area as well. So surface area actually affects the rate at which a chemical reaction occur, right? It affects it. That is surface area. So it also affects the rate at which a chemical reaction is going to occur. Now, what I'm basically saying is that whenever you increase, whenever you increase what the surface area, let me just say SA. Whenever you increase the surface area, increase in surface area will follow increase in what in the rate at which what particles of reactants are going to collide together. So whenever you increase the surface area of a reactant, it's going to enhance the rate at which they are going to collide together. That shows that in that scenario, rate of reaction is going to what is going to be increased. That is, the reaction rate will be what will be enhanced, right? So whenever you increase the surface area, it's going to increase the rate of what of chemical reaction, and that's actually has to do with, let me just use this one as an example. Let's say we have what we have charcoal, or we simply say coal, right? So whenever you have charcoal in its what in its let me just say more complex form, that is whenever you have it in a shape, it has a shape like this, it have it, let's just say it have a particular shape, then you actually light it with fire, you actually let me just say you expose it with what is fire, the rate at which the charcoal is going to catch fire will be very 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 slow compared to when you grind the charcoal. So by grinding the charcoal, that simply means you have increased the surface area, and that simply shows that whenever you increase the surface area of a reactant, it's going to increase the rate of chemical reaction. But whenever you do not increase surface area, or simply let me just say the surface area you decrease it, is going to decrease the rate of chemical reaction. So that's it about surface area. Now let's simply move to the next one, which is actually that of uh, the case of, let me simply say, we have the case of let's say catalyst in this case. So although I'm going to explain the effect of catalyst separately, but let me just talk about it in this scenario. Now, one thing about catalysts is that catalysts are actually, they speed up the rate of chemical reaction. That's actually what catalyst does. So they speed up the rate of chemical reaction, the rate at which reaction occur, the rate at which reaction occur. So that's the function of what of catalyst. That's function of catalyst. They basically enhance the rate of chemical reaction. And in that scenario, whenever a reaction occurs, for example, the case of hydrogen peroxide, right? Hydrogen peroxide, in the case of what? In the absence of catalyst, whenever there is absence of what? Of catalyst, it's actually very, very slow to decompose. It's decomposed at a slower rate. And it's basically decomposed to what? Into H2O and also what? O2. But one thing is that the rate at which it decomposes is very, very, very slow. So that's just it. But whenever there is what? There is catalyst, presence of catalyst, the rate at which this hydrogen peroxide decompose is very very fast. So catalysts actually enhance the rate of chemical reaction, right, by actually affecting the rate at which the particles actually collide. Don't forget that surface area also affect the rate at which particles collide as well, because increase in surface area will enable the reactant particle to be able to collide very very well. That is, they will be able to react to each other very well. But in the case of catalyst as well, it's basically enhanced, right? It's enhanced the particles, that is the rate at which particles of the two reactants actually collide together. And one thing about catalyst is that it acts by lowering lowering the activation energy, that is the energy barrier, the activation energy. So that's the reason why I'm going to explain catalyst in details in a separate video. So but just know that the presence of catalyst actually increase the rate at which particles of reactant actually collide together. So that's another effect of catalyst. Now let's talk about the temperature as well, right? Let's talk about the temperature, because temperature actually is also very very important. So that's just it. So as far as temperature is concerned, temperature also affect the rate of chemical reaction, because whenever we increase temperature, it's going to increase the rate at which particles of reactants actually collide together, right? That's why that increase in temperature will speed up the rate of chemical reaction, right? But one thing about temperature is that we have some reaction that cannot occur on their own. Such reaction actually require temperature, right? In form of what? They require energy to break their bonds into form of what? Of heat. And that has to do with what? With temperature. So increase in temperature of a reactant will actually break the bond between the reactant particles, Then whenever you have a reactant that are tightly bound together, let's say you have that of A in solid and that of B in what, in solid, and it actually gives rise to what, to, let me just simply say, C. And let's hope our C is in what, is in liquid state. And in this case, you actually apply it, or you apply temperature. Let me simply use temperature. Whenever you apply temperature, what will basically happen is that the particles that are found in what, in this reactant A and B will be broken, like they will be break together. The bond that attach the particles together, that, the bond of solid is actually tightly packed. So the bond will be break down, and in that scenario, the particles will be free to move about. So when the particles are free to move about, that shows that they cannot collide successfully according to collision theory. So once they collide together, the rate at which the particles of the reactants in the presence of it are going to collide together will be very, 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 very fast, right? Because temperature is what is involved. So increase in temperature will basically increase the rate of what, of chemical reaction. So that's just it. Now let's move to what, to pressure. Whenever you're talking about pressure, pressure is mostly applicable to what, to gas, right? So increase in what, in pressure actually increase the rate at which what, at which reactant particles in gaseous state actually react with each other. So by increasing the what, the pressure is going to enhance the rate of what, of chemical reaction, and that's just it. So that's just it about this temperature, catalyst, surface area, pressure, and also what, nature of reactants. But everything actually has to do with what, nature of reactant, whether it is what, solid, liquid, or gas. But just so that these factors actually affect, according to what, to collision theory, particles of reactants must collide together for a reaction to what, to occur. So increase in any of these factor will actually increase the rate of chemical reaction. That is just it. Now let's move to condition of the reactant, because there is more to talk about condition of reactant. Then we now go ahead and pick each and every factors one by one, because they have their calculation. Now let's talk about the condition of reactant now. Now, according to concentration of reactants, right? So we have the first one, which is concentration of reactants. Concentration of reactants. So what I want you guys to know is that concentration of reactant actually affect the rate of chemical reaction actually, but it affects it in a more positive way if there is increment in what, in concentration of reactants. So that's actually what it means. But in this case, whenever you're talking about concentration of reactants, so almost all reaction actually occur at faster rates. They occur at faster rates if a concentration of reaction is what, is increased. Now suppose we have a reaction. Let's say we have reaction A plus that of what, of B, right? Then plus that of what, of C, right? To give us let me just simply say D, and in this case we represent our D as what, as Y. So this N, M, P, and also Y actually represent what, the stoichiometric ratio in this case. And in that case, let's say this reaction is actually what, proceeding, is occurring at what, as a slower rate. As a slower rate. One thing that happens is that if we increase any of the reaction of this, because in chemistry there's something that we actually refer to as limiting reagent, and also what, excess agent, right? What actually determines the rate of chemical reaction is actually the what, the limiting reagent, because once it's finished, that shows that the concentration of the reaction we actually remain instant. That is, it will remain constant. And in that scenario, the nature of the reaction will be determined by what, by the excess reagent, because it's just like you talking about acid and base. If you increase the concentration of an acid, that shows that there will be more of acid than that of what, of base. In that scenario, that shows that base is actually what, the limiting reagent, right? Because it determines what, the rate at which the reaction is going to occur. But what will determine the original nature of the reaction is what, is the excess reagent. So whenever you increase the concentration of any reactant in a chemical reaction, it's going to enhance or speed up the rate of what, of chemical reaction, right? So that's actually that most reaction. That's actually the reason why most chemical reaction, they proceed faster if any of the concentration of the reactants is increased, right? So that's actually what happened here. But what I want you guys to understand is that there's actually a common relationship between the rate of reaction and what, concentration of what, of reactants. That is, there's a relation between the rate of reaction and also what, the concentration of the reaction. So there is actually a relationship between them, right? Now, according to this one that we have here, now look at this one. So what actually happened is that here is that, if you look at this now, We have reactant A, reactant B, and reactant B, and reactant C. But we have a single product here, which is what? Which is D. Right? Now, what it's happening here is that reactant A, B, and C, they are going to decrease it with what? With time. Right? They will decrease with time. And reactant D is going to what? Is going to increase with what? With time. Why this is going to what? Decrease with time. Now, in that scenario, since reactants A, B, and C, they are going to decrease with time, right? So we can actually say that the rate, we can say that the rate of disappearance of what? Of reactants, right, is actually is equal. Let me simply use the word equal here. Is equal to the rate of appearance of products. Because according to this reaction, it's actually said that these reactants are going to decrease with time, while the product are going to what? Increase with time. In that scenario, if we increase any of the concentration of the reactants, it's going to determine the nature of what? Of the reaction. So that's why that concentration of the reactant actually has a great effect when it comes to chemical reaction. And we have some factors like what? Like the rate expression. Rate expression. What rate expression, or you simply say rate law, actually indicates here is that it actually shows you what? The relationship between what? Between the rate of reaction and also the what? Concentration of the reactant. Concentration of reactant in this case. Non reaction. Concentration of the reactant and also what? Rate of reaction. So that's actually what's happened here. So another thing I'm going to talk about is actually when we are talking about the case of what? Of reaction rates. Now look at this. Let's say we have the reaction rate for this particular expression. That's going to give us what? Negative change in what? In concentration of what? Of A, right? Divided by what? N change in what? In T. This is going to be equal. We are going to have negative change in what? In concentration of what? Of B, right? Divided by what? This is going to be what? M change in what? In T. Then this is going to be equal to negative change in what? In concentration of what? Of C, divided by what? Minus, let me simply say this is not minus actually, because we've already indicated minus here again already. So in that scenario, we're going to have this is going to be P. We're going to have it to be P. Then we are going to have what? Change in T. Then followed by this is going to be equal to what? Positive change in what? In concentration of what? Of D, divided by what? We're going to have Y change in T. Now look at this. This is actually the rate of this reaction. This is basically the rate of what? Of this reaction. And what does it mean? It actually shows that concentration of the reactants is decreasing. That's the sense of you seeing the negative here. That is, the reactants are going to what? Decrease with time. Why? As far as this one, we are going to have the products which are going to what? Be increasing with time. So due to this reaction rate, that is the rate of what? Of this reaction that you are seeing here, the rate of reaction can be determined by the concentration of reactants. That is, the concentration of reactant can determine the rate of reaction. That is how fast a reaction is going to be. And I'm going to give you an example, because from this scenario, you can actually take note that the rate of reactants, right, is always equal. The rate of the disappearance of reactants is always equal to that of what? Appearance of what? Of product. In that case, rate at which negative change in the concentration of A, of this guy here, which is the rate of what? Of reactants A is decreasing, is also the same as what? The rate at which what? The product is what? Is increasing, right? So the rate at which individual reactants A actually decrease is equal to the rate at which what? This product is what? Is increasing. That's exactly what reaction rate means. So concentration of reactant has a great effect on rate of chemical reaction, and I'm going to show you an example now. So suppose we have let's say we have a reaction. Let's say we have a reaction, right? And in this case, let's say the reaction has to do with what? Let me just say we have hydrogen iodide, right, in gaseous state, right? Then this actually dissociates into, let me simply say we have hydrogen gas in gaseous state as well. Then we have what? Iodine gas, right, in this case. So in that scenario, look at this very well. If I try to balance this equation, right, using simply the stoichiometric ratio, right, I'm going to balance the equation. If I balance the equation, I'm going to add 2 to this side. And look at it very well. So if I'm trying to write the rate of reaction for this scenario, if I'm trying to bring out the rates, I'm going to say this is basically we're going to have negative change in what? In constant what of Hi, right, divided by what, this is going to give us 2 multiplied by change in what in T. Then this is equals to what, then positive change in what, constant what of hydrogen gas, then divided by what, change in what in T. Because this, the supplementary here is what is 1, so I don't need to what indicate the 1 here. So we're going to have this to be equal positive change in what in constant what of iodine gas, or you simply say iodide. So we are going to have this one to be changing what in T. Now look at this very well. So do you know what this reaction simply means? It simply says that the rate of disappearance of hydrogen iodide. Let me simply say hydrogen iodide in this case. Let me represent very well. So here we're going to have hydrogen iodide. The rate of disappearance of hydrogen iodide, which is Hi, is twice the rate of appearance of hydrogen gas, right? Of hydrogen gas, or you simply say hydrogen gas and also what? Iodine gas. But what you have to know here is that, well, if I'm relating this hydrogen iodide and also what hydrogen gas together, so the rate at which this Hi actually decrease is twice the rate at which was this hydrogen gas what is formed, right? So that's actually what the rate expression actually, what the rate constant is actually what is expressing, the rate equation. So now in that scenario, now if you look at it very well, so due to from this stoichiometric ratio, I can actually determine the rate of what of chemical reaction. That shows that the constant of reactants or the molecules of reactants here actually determine how fast the rate of reaction is going to be. Because here we are having 2, we are having 1 here, and we are having what 1 here. So from there we simply derive the rate of disappearance of Hi, and we also determine the rate of appearance of H2, which is hydrogen gas. So constant of reactants has a great effect in determining the rate of chemical reaction, right? So another thing I would like to write out is actually what the rate experiment with respect to what H2. So when I'm writing it, I'm going to have R ATE, which is the rate, is going to be equal negative change in what in Hi, right? Then I'm going to have divided what that's going to be 2 change in what in T is equal to change in what, let me just put positive here, constant what of H2, right, divided by what change in T. That is when I'm trying to relate what hydrogen iodide and also what hydrogen gas together. So in that scenario, as you can see, the rate at which this Hi is what is decreasing. That's why you are seeing the negative here, is equal to the rate at which what this hydrogen gas is what is increasing, right? So this is half, actually this is half here and this is 1 here, right? So half divided by 1 is still what is 2, right? So that shows that the rate at which what Hi is what is decreasing is twice the rate at which what hydrogen gas is what is increasing. So the negative sign I've explained earlier, that is, it shows what the reactance is what decreasing, whereas the positive side actually will indicate that what the product what is increasing. So that's just it. So now, according to this reaction, if I'm asked to write what the rate expression for this reaction, right? So rate expression is actually like an expression that relates what the concentration of the reactant with the rate of chemical reaction. That is, with the rate of reaction. Now in that scenario, if I'm asked to write what the rate expression for this, I'm going to simply have it to be expression that equals to rate constant K, right? Then here, as far as this is concerned, then this is going to be what Hi raised to the power of X. So this is basically what the rate expression. Rate expression, if you look at it very well, is basically like helps to show the relationship between the concentration of the reactant and also what concentration of the reactant and also the rate of reaction. So that's basically what you are seeing here. But these parameters, with this case, is the rate constant. That is the rate constant, which indicates that whenever you are increasing the concentration of this Hi, the rate constant is going to remain the same, but the rate of reaction is going to increase, right? If you choose to increase it, and this X simply represents what the order of reaction, and what order of reaction is that it's taken to be what the power of concentration, the power of concentration of the reactant. And in that scenario, this X can only be determined experimentally. This K can only be determined experimentally. But what is this 2 called? This 2 with reference to hydrogen iodide here is actually called what? the molecularity of reaction. Molecularity of reaction, because it can only be determined through balancing of what of equation. You can simply balance it. But one thing that happens is that this molecularity of reaction can never be what? It can never be zero. That's one thing about molecularity of reaction. But order of reaction here, it can be what? It can be zero. So that's why that there is difference between what? Between the molecularity of reaction and also the order of reaction. You can't just say because 2 is here, you have to put 2 is here. This is not equilibrium, right? But one thing is that this is chemical reaction, and this X has to be the order of reaction. And it can be only determined experimentally. It can be zero, but molecularity of reaction can never be zero. So I'm going to explain the differences in a separate video, right? So that's just it about this video. But one thing is that when you see rate equals to KHI, this basically was the rate law, right? And it basically shows the relation between the rate of reaction and also the constant of the reactant. That's what happened. So that's just about the factors affecting the chemical reaction as far as constant is concerned. So I'm going to show you guys how to solve question under the constant of reactant, because whenever you have increase in constant of reactant, it's going to increase the rate of chemical reaction, and at the same time, whenever you have decrease in the constant of reactant, it's going to decrease the rate of chemical reaction in some cases, and all has to do with what? With the nature of the reactant actually. And don't forget that nature of reactant and constant of reactant in turns affect the particles of reactant as well. They affect the particles of reactant. I think they affect the rate at what the particles of reactants actually collide together. So that's actually what I'm going to say in this video. So in the next video, I'm going to show you guys how to solve question under the constant of reactant, because there are many questions here that makes up of this molecularity of reaction, order of reaction, rate constant. We have the constant of the reactant, and also what rate of chemical reaction itself. So I'm going to show you guys how to solve it, and that's just about this video. So if you enjoyed this video, please do well to like, share, and don't forget to subscribe to my YouTube channel. And most importantly, kindly support me in my Patreon page. So I'm going to drop the link in the description button below, so you can actually check out the link and make sure you have access to this with the full video on this chemical reaction. That is, I made a lot of video on it, and if you want to have access to the full video, you can actually visit my Patreon website or Patreon page. You are going to see the link in the comment section below. So thanks for watching.